So now we have theory portion. This is about actually mean value theorems. The first theorem is Rolle's theorem. So you take a theorem says that you take a continuous function. So let f be a function from closed interval a b to R such that the function satisfies the following three conditions. F is continuous, it should be continuous on closed interval a b, that means there should not be any break. Second condition is f is differentiable on open interval a b. At endpoints differentiability is not important. The third important condition is find the value of the function at a and find the value of the function at b. These two should be equal. If function satisfies these three conditions, then this is a conclusion. Then we must have one point C. Then for C from open interval AB, we can have at least one C from this such that f dash C is 0 for some C from open interval AB. This is the concluding line. Function is continuous on the closed interval AB, differentiable on open interval AB, f of A, f of B both are equal. Then you can find one C, at least one C, minimum one C from open interval AB such that at that place the derivative becomes 0. Now what's the meaning of this? Let me see the meaning of this theorem. So this says that you take a function like this here, which is continuous differentiable. Suppose this is A, this is B. Function is like this, for example. You can see that this is a continuous, there is no break and there is no corner like this. So it's a differentiable. F of A here, f of B here. So f of A equals to f of B. You have function like this that satisfies all the three conditions. Now then you can find one C. So this is one C anywhere from this open interval AB such that if you have this point on the curve function C comma f of C, then you can draw a tangent here at this place. This is the tangent at C comma f of C. Now if you remember, or you will learn later on, f dash represent slope of the tangent. This you will run. F dash derivative represents slope of tangent. This you will learn later on. Derivative represents slope of the tangent. What's the slope of the tangent here? 0. Now you know slope of the x-axis is always 0. So tangent must be parallel to x-axis, and here tangent is parallel to x-axis. So it says that here geometrically tangent at C comma f of C is parallel to x-axis. Tangent at C comma C is parallel to x-axis. That is precise meaning of Rolle's theorem. Function should be continuous, differentiable, and f of A equals to f of B. Then you can find one C from the open interval AB such that f dash C is 0. Now f dash C is 0 means what? Slope of the tangent is 0. Now which line has, recall 11th standard coordinate geometry, which line has slope equals to 0? X-axis. You know slope of x-axis is 0. Slope of x-axis 0, that means this tangent must be parallel to x-axis. So this is interpretation. Tangent at C comma f of C is parallel to x-axis in case of Rolle's theorem. Next is mean value theorem. That's sometimes called MV theorem. This is generalized form of Rolle's theorem. So let's take a function. Let f be a function from closed interval a b to r such that here we have first condition same as what we had in previous theorem. F is continuous on closed interval a b. Second one, f is differentiable on open interval a b. These two conditions are same. Continuous on closed interval, differentiable on open interval. Now we don't require third condition here, direct concluding line. Then for some c from open interval a b, you can find c from open interval a b satisfying this condition, f of b minus f of a upon b minus a. This looks like slope if you remember, y2 minus y1 upon x2 minus x1 equals to f dash c for some c from the open interval a b. This is the conclusion. This is the concluding line. Function must be continuous and differentiable. Then you can find 1c from open interval a b such that f of b minus f of a upon b minus a equals to f dash c. This is always true in case of mean value theorem. Remember, in case of Rolle's theorem, f dash c was 0. Now what is the meaning of this? Let me write the meaning of this. So here, meaning of this theorem. So you need to take a function which is continuous and differentiable. F of a need not be same as f of a b, like this. Here a, so we'll get the f of a. This is b, so here we'll get f of b. So you can see that f of a is not same as f of b. What are the coordinates of this a comma f of a? What are the coordinates of this b comma f of b? Now if you recall 11th standard, find the slope of the line joining these two. Let me call this as a and b. So what's the slope of the line joining these two? y2 minus y1 upon x2 minus x1, that is LHS. y2 minus y1 upon x2 minus x1, left hand side. What is f dash c? You know that it is the slope of tangent. So what you are saying here, that the slope of tangent and the slope of line of joining these two are equal. That means these two must be parallel. So you can have one point C from the open interval AB like this. You must have C that tangent is parallel to line joining these two. So tangent must be like this. This is line joining these two. So you can have one point C here. This is a point C, and the coordinates of this point is C comma f of C. So tangent at this place for some C from the open interval AB such that tangent is parallel to line joining these two. Tangent is parallel to line joining A comma f of A and B comma f of B. So when you have tangent parallel to line joining these two, means it is a MV theorem. And tangent parallel to x-axis means it's a Rolle's theorem. So these two things you need to keep in your mind. Here conclusion is this. In sums we use this, remember. And in Rolle's theorem, what's the conclusion? That is f dash c is 0. So after doing these two things, now let's go to exercises. So exercise 5.8, you are given this function on this domain. This is like closed interval AB. The question is verify Rolle's theorem. So we need to check for these three conditions. Clearly, f is continuous and differentiable. differentiable. Why? You can see that this is a quadratic, means in general polynomial. So I'll write as it is polynomial function. In fact, it is quadratic. Every polynomial function is always differentiable and continuous. You can find the derivative of this. So differentiable, and every differentiable is continuous, so it's a continuous. So reason is this. Third condition for Rolle's theorem. You find f of minus 4. So 16 minus 8 minus 8, it is 0. Find f of 2, which is 4 plus 4 minus 8, which is 0. So therefore f of minus 4 equals to f of 2. Third condition. First continuous, differentiable, and this, and therefore you can say that Rolle's theorem is applicable. Rolle's theorem is applicable. I mean, you can use the Rolle's theorem, and therefore we must have f dash c equals to 0 for c from open interval minus 4 to 2. Minus 4 to 2. So therefore, what is f dash c? First get f dash x. What is f dash x? 2x plus 2. So here your 2c plus 2 equals to 0. And therefore c plus 1 equals to 0. And therefore c is minus 1. So this is the point. If c equals to minus 1, then tangent is parallel to x-axis. Right? This is what you have to do in Rolle's theorem question. We got the c. You can find one c from open interval minus 4 to 2 such that f dash c becomes 0. So what I did, I just differentiated 2x plus 2. Then instead of x you put c. 2c plus 2 dividing by 2. C plus 1 is 0, so c is minus 1. Question number 2, there check whether Rolle's theorem is applicable or not. Now your first function is box function from 5 to 9. So if you recall, here even first condition doesn't hold. Box function is discontinuous at every integer, so it's not continuous, so you cannot use the Rolle's theorem. But directly you can see the third condition. What is f of 5? That's a box of 5, which is 5. And what is f of 9? Which is box of 9, which is again 9. So these two are not equal. F of 5 is not equals to f of 9. So f of a is not equals to f of b. So therefore you can say that Rolle's theorem is not applicable. You cannot use Rolle's theorem. It must satisfy 3 conditions, then and then it is applicable. Question number 2 is same. I'll go to third question. If x equals to x square minus 1 on this domain 1 to 2. Now you know that this is a quadratic. F is polynomial function. Polynomial function. Let me write here. F is polynomial function. You know that therefore it is differentiable and continuous. So therefore f is clearly differentiable and continuous. First 2 conditions holds, remember here. Now go to third condition. Find f of a, that is f of 1. 1 minus 1, 0. Go to 2. F of 2. 4 minus 1, 3. Are they equal? No. So f of 1 is not equals to f of 2. And therefore what is the conclusion? Again, Rolle's theorem is not applicable. Rolle's theorem is not applicable. You cannot use Rolle's theorem for this because first 2 conditions hold, but third condition doesn't hold. Example number 3, this is an important example. You have a function from minus 5 to 5 2r, so this is the domain of the function. You are given that derivative of a function is non-zero for every x and you want to show that these two are not equal. So we do by contradiction. We assume that by contradiction, assume that f of minus 5 equals to f of 5. This is our assumption. And f dash x is non-zero, that's given to you. That means derivative exists, so f is differentiable. What is given to you? Derivative is non-zero, but you can find the derivative. That means it's a differentiable. And you know a theorem that if function is differentiable, then it has to be continuous. Therefore f is continuous. So what you are seeing, if you look at this, function is continuous, function is differentiable, and f of a equals to f of b. From 1, 2 and 3, you can say that the Rolle's theorem is applicable. Rolle's theorem is applicable. I repeat these three arguments. You want to show that here f of a is not equals to f of b. So by contradiction, I'll assume that f of a equals to f of b. 1. Call that as 1. You are given that f dash x is non-zero. But f dash x is there, remember, it may be 2, 3, 400. That means function is differentiable. If function is differentiable, then it has to be continuous. So therefore f is continuous. So if we look at this 1, 2 and 3, function is continuous, differentiable, and f of a equals to f of b. Therefore Rolle's theorem is applicable on, let me write, minus 5 to 5 for the function f. And therefore there is c from minus 5 to 5 such that f dash c is 0. Now, which is contradiction? You are saying that f dash x is always non-zero for every x in the domain. So which is contradiction? Which is contradiction to f dash x is non-zero. In the hypothesis, I mean the data itself, you are given that the derivative is always non-zero for every x. Here you are concluding that there is some c from the domain for which f dash x is 0, which is contradiction. And why we are getting this contradiction? Because of this assumption. So these two cannot be equal. Therefore f of minus 5 is not equals to f of 5 is proved. Question number 4, you want to verify mean value theorem. So here f is polynomial function, as we have noted. And therefore, being polynomial, it is continuous and differentiable. Therefore f is differentiable and continuous. You doesn't require here third condition, that is f of 1 and f of 4. Remember, for mean value theorem we just need these two conditions only. Okay, now you can write therefore mean value theorem, MV theorem is applicable here. Remember, you can use mean value theorem here. What it says, therefore f of b, that is f of 4 minus f of 1 upon 4 minus 1 equals to f dash c for c from open interval 1 to 4. Mean value theorem is applicable, and therefore you can find 1c from open interval 1 to 4, for which this is equals to f of b, f of 4 minus f of 1 upon 4 minus 1. Now what is f of 4, which you can find from here, which is 16 minus 3. What is f of 1? 1 minus 4 minus 3 upon 3, which is equals to f dash c. What is f dash x? Which is 2x minus 4. So you have 2c minus 4. Repeat this. I'll repeat this. So here, what is f of 4? Just place here 16 minus 16 and 3. What is f of 1? 1 minus 4 minus 3. What is f dash c? First find derivative, which is 2x minus 4, and then instead of x you put 1. So here this is minus 3. Here you will get the minus 6, so this will be plus 6 by 3 equals to 2c minus 4. So this is just 1 equals to 2c minus 4. So therefore c is 5 by 2. This is the value of c for which f dash c becomes this f of b minus f of a, and here mean value theorem is applicable. So you are given this function on closed interval 1, 2, 3, and you are asked to verify first mean value theorem. So here again f is a polynomial function, and you know every polynomial is always differentiable and continuous, and therefore f is differentiable and continuous on closed interval 1, 2, 3, or you can just write differentiable and continuous. Okay, now you here for mean value theorem you doesn't require third condition, therefore you can say that mean value theorem is applicable. You can find c using mean value theorem. So therefore f of 3 minus f of 1 upon 3 minus 1, f of b minus f of a upon b minus a equals to f dash c for c belongs to open interval 1, 2, 3. From c belongs to open interval 1, 2, 3. So here upon 2, 3 minus 1. What is f dash x? You know f dash x is here 3x square minus 10x minus 3. 3x square minus 10x minus 3. So here it will be 3c square minus 10c minus 3. Just instead of x you put c. 3c square minus 10c minus 3. And you find both the values here. F of 3, just put x equals to 3, minus find f of 1, put x equals to 1. Simplify and get the c. Right? It's a quadratic equation, so we'll get the maximum 2 values of c, but c should be from 1 to 3 only, remember. Further, you are also asked here one more sub question, find c for which f dash c is 0. So indirectly you are asked for Rolle's theorem. So f dash c, you know it is this one, 3c square minus 10c minus 3 equals to 0. C always comes from open interval of the domain, remember, open interval 1, 2, 3. So factorize this. So we'll get 2 factors of this and get the value of c. C should be from 1, 2, 3 only, remember. In case c is 1, that's not the required value, because here open interval 1, 2, 3 you are given. So do this. Last example, mean value theorem for all 3 functions given in the question 2. So there, go to first function, fx equals to box of x on closed interval 5 to 9. Now you need 2 conditions for mean value theorem, differentiability and continuity. We know that this function is, we know that fx equals to box of x is not continuous, even not differentiable also, not continuous at every integer, that is 6, 7, 8, at every integer it failed to be continuous, and therefore therefore mean value theorem cannot be used here. Cannot be used. Second function, same here. You can give the same argument, that's also box function. So for box function again mean value theorem cannot be used because it's not continuous. You did it in beginning of this chapter. Okay, third function, let's see the third function. Their third function is fx equals to x square minus 1 on domain 1 to 2. Now here you are given polynomial function x square minus 1 which is quadratic, so which is always continuous and differentiable. Here f is a polynomial function, and therefore f is continuous and differentiable. Remember, everywhere continuous and differentiable, and you require just two conditions for mean value theorem, and therefore mean value theorem is applicable here. You can use the mean value theorem and you can find C. Rolle's theorem is not applicable, we already discussed, because f of 1 is not equals to f of 2. You can see this, f of 1 is not equals to f of 2. So earlier we have noted that third condition doesn't hold, and therefore Rolle's theorem is not applicable. But mean value theorem is applicable because there we require just two conditions, continuity and differentiability. Now you can find the C. So for C belongs to open interval 1 to 2, we have f of b, that is f of 2 minus f of 1 upon 2 minus 1 equals to f dash c. Okay, what is f of 2? That is 4 minus 1, which is 3. What is f of 1? Which is 0 upon 1 here. And f dash c, what is f dash x? That is 2x. So this is 2c. So and therefore c will be 3 by 2. This is the value of c here. So in this third example, Rolle's theorem is not applicable, but mean value theorem is applicable.